10 times 50. Earth 2, G is equal to 10 meters per second squared.
.62 meters per second.
All right, that's how fast he's going at the bottom. Questions before I make it seem different?
So if we wanted to, because Giovanni said height was 0, we could have either way made initial height 0?
Yes,
Okay.
in which case the final height would have been negative 50.
So we have a final speed, but.
Well, that's the final speed right there, we calculated. Realize that if we had done Newton's laws for this, because y is constantly changing direction as it goes down, we have a constantly changing net force acting on him. His acceleration is not constant as he does this. So the beautiful thing about energy is that we really don't care about what happens in the middle, we just care about what's the beginning, we can predict what's gonna happen at the end, assuming non-conservative work is 0. Pardon? Yes.
So when this problem is downward positive,
Doesn't matter.
why would it not matter?
When dealing with gravitational potential energy, the farther you are from the ground, the center of the earth, you're gonna get a higher number. So whatever value we put down here, this is 50 more. So if that's 0, this is 50. If that's 100, this is 150.
Okay.
Regardless of what we make positive or negative.
But is it possible to get a negative final velocity?
This is a speed, so no.
Because, okay.
All right, let's make the problem seem difficult. Bob enjoyed that so much he decided to go back to the top. And I'll let you decide whether Bob is a pronoun or a name. So he's coming along, and suddenly, what he doesn't realize is that there's been a cave-in. Uh-oh.
So Bob's dead.
Didn't true. Oh, wait, not yet.
So he has airtime at this point,
So there's a cave-in,
Alright.
and now, just to make sure that, so you know that Bob is safe, there's clouds, cotton balls, and kittens down here.
He's gonna squish kittens when he falls.
No, he's gonna land on the cotton balls and the clouds, the kittens are gonna rescue him. They're gonna tell him. Now, I would say cats, and need to land on cats, but who would care, right? You know what I'm saying?
So he
Who cat
didn't.
people in here?
So he didn't make it across.
I had a student once who had a cat, and I made a comments, anti-cat statement. And she goes, "Hey, wait a second," and I said, "No, I've heard you complain about your cat so many times. You're not- Can't object."
I mean, cats scratch you. I've seen people get so many scratch from their own cats.
I mean,
Dogs don't do that.
no, when
No,
it's
dogs-
well,
You're a cat.
I like cats, but
Scratch marks for my dog to say otherwise.
well, when I pass by a dog, sometimes walking to like my bus stop or something, it would always chase after me for some reason.
Okay, so how fast is he going? How fast is Bob going when he hits the cotton balls and clouds?
0.
How
Not
fast
0.
Is he going? Is he going the same speed?
So you're saying he's 31.62 meters per second?
I think it would be more.
Why?
Was it before the thing?
because technically wouldn't that speed be like the highest speed he's gone through? It won't be like exactly like during the whole time he's going 31. miles per second, right, meters per second?
Yeah, this is the
So-
speed at the very end.
At that point,
The
is
reason
he
I
airborne, since he's falling into that?
He is airborne, but there's no air resistance.
The,
Or?
the reason I think he just is going the same speed, which I could be wrong, the reason I think is because the main factor affecting the outcome is the acceleration due to gravity, right?
Sorry, I missed it. Somebody distracted me. Yes.
I think I forgot to put my name on mine. Can you mark it really fast? Yeah.
I might have even spelled it right. And if you notice from the blanket, she's the one who has the blanket.
I know, I know.
Okay, I'm sorry, Laura.
So the initial height is still the same.
Correct.
The initial the height of the ends is also still the same.
Yes,
The distance traveled is different.
correct.
However, the speed at which it goes would also technically still be the same, because the factor affecting it is the acceleration due to gravity, the G, right?
Yeah, I would have expanded to the only force acting on him that's doing any work is the weight.
Yeah.
The normal force, while he's still on the slope, the normal force still is not doing work because of the perpendicularity. But once he's in the air, it's only the force of gravity. But nothing changes here. So yes, spot on.
Question.
What is different though? The speeds are the same, but obviously these are two different situations.
The time.
Okay,
The height he's falling from?
It's still
they still starts at 50 meters above.
Yeah, the once he goes down, that's where it's falling from there.
Oh,
Would the initial result velocity would still be zero?
Dr. Fox,
yes.
she says displacement.
She said what?
She said displacement, she just isn't confident in it, so I'm being confident for her.
Okay, displacement is different, yes. Apparently you're not reading my mind well today.
It's all the line that you're left.
Oh,
Yeah.
Is it the type of work that's, no.
velocities are different. Speeds are the same. I mean, the other things, yes, but the speeds are the same, but the velocities are different. Because here, he's going this way, and over here,
He's going down.
at some angle like that. And I can give you more information, we can calculate it, it's a projectile motion problem, not the topic at hand. Ritika,
What if I just used common sense? Would this make sense? Like, he's at the same speed if he fell in there, or if there was no.
yeah, if you're looking at the equation here, the only variables, I guess starting from here, or which got us to here, the only variable is what that initial height is.
Okay.
So as long as he's falling the same distance,
He's at the same speed.
yeah, assuming that there's nothing detracting from that. There's no non-conservative work. Okay, Giovanni, you have your hand up.
Wouldn't the kittens eat him since they've been in that cave for so long?
They're nice kittens.
But they're hungry.
They've eaten the cats.
Well,
But again,
So per se, if the final spot was like, I don't know, like lefted or something by like 30 meters, then the
as in,
acceleration.
it
would
comes
be
back up again.
Sure. So then, would the displacement, like the speed would be different?
Yeah, if he came back up, the speed would be different. Because then the initial height is 50, well, depends on where we want to make
No,
zero,
so
but
like-
there's a 20-meter difference then if he comes back up to 30.
So not like thinking about, like, if it was just like, per se, this was like where it is, right? So there's something keeping the tip of it up, right? So it's technically the end would be higher than the actual like ground.
So as it just curls up just a little bit. We are out of sync right now, I think.
It's okay, go with your question.
I was just gonna ask, so in this scenario, the speed is the same, but the thing that would make it different, like if we weren't doing a frictionless drop off where you put the,
Yep.
it's on ice, so it would be frictionless at the point which he's falling into the hole. But then, so that would be what would change the
Yes,
speed?
because the distance traveled is different. Yeah, we would have to figure out, if we bring friction into it, and friction generally on a problem like this, I either have to tell you, here's the average friction, or I have to make it straight so that you can calculate what the friction is and then give you the coefficients. All right, I'm about to add another twist to it.
Another hole with kittens?
All right, the kittens rescued him. They told him about a secret passage that with steps up here, so he climbed back up and he's doing it again. Now, while he was walking back up, it snowed and filled in the hole again. Kittens are safe. They're over here in the
Oh,
cave.
yeah, sure, magically.
So now also while he was working his way up, it took a while for him to do this. There were snack bars along the way. They installed a spring down here.
So he will recoil.
So he's gonna hit the spring. Now the spring, you need some idea of how stiff is the spring. This is what is known as the spring constant. So the spring constant is, we'll just say 20 newtons per meter. In other words, it takes 20 newtons to compress it,
To one.
1 meter, 40 newtons to compress it 2 meters, 60 newtons to compress 3 meters and so forth, or stretch it. It takes 20 newtons to stretch it 1 meter, 40 to stretch it 2 meters, and so on. We will definitely get into more detail about spring constants, but that's for a later chapter. So what I want to know is how much will the spring compress? It is ideal, which means it will not interfere with itself. And if you've played with a slinky, you know that you can only compress a slinky so far. It is not ideal. This is ideal. It will not interfere with itself. We're going to go through the exact same process as we did before. This is an ideal spring. It is conservative. Weight is still acting on him, conservative. Normal force is acting on him, non-conservative, but still not doing any work. So, yada, 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 energy initial equals energy final. Well, same step as there. Kinetic energy initial plus potential initial equals kinetic final plus potential final. Kinetic energy,
Half
One
mv
half
squared.
mv squared.
if you're gonna do a syllabus course of angels, take notes from. Now the formula for potential energy, I have two conservative forces, so I have two potential energy formulas. The one associated with weight,
And the spring.
yeah, what is the one, sorry,
MGA.
thank you.
And then would we just multiply
And the one associated with the spring,
20 newtons per? Is it just 20?
no, that's a constant that we'll go into.
One half
One half.
k.
Delta x squared.
Initial. A equals, and then the finals over here, 1/2 mg final squared plus mg h final plus 1/2 k delta x final squared. What is equal to 0?
Initial speed. The final displacement. Same in there.
The final delta x,
Not the final height.
the final height,
Yeah,
y,
just I said so.
okay.
The initial displacement.
Of the spring,
Yeah.
okay. Yeah, the spring's just sitting there.
Mhm.
It's, as a former colleague, Jim B12 said, that's unhappy. We got one more.
We can,
Get rid of.
oh, okay, guess, yeah. Wait,
Is it
so,
final velocity? Is the final velocity 0?
Yeah. We want to know how much the spring is going to compress. It will keep compressing until he stops.
oh, I thought you were gonna bounce back.
Before he bounces back out.
Yes.
Okay.
So we've reduced this down to mgh initial is equal to 1/2 k delta x final squared. We're trying to find delta x final. We cannot get rid of mass now. Yeah, Giovanni?
What happened to the 1/2 K in the first half?
The spring is just sitting there. It's not stretched. It's in equilibrium.
Also, the whole thing's off.
Yeah. Delta x is how much the spring is displaced from its equilibrium position. And we're assuming that it's just starting out sitting there. So now it's a plug and chug. At this point, we do need to know the mass. Let's give him some generic adult US mass of 70 kilograms. So I have 70 times 10, because I think I put this on Earth 2, times the final height is 0, the initial is 50, equal to 1/2 times 20 times delta x final squared. Doing the fancy math here, this is 35,000 is equal to 10 delta x squared. So 3,500 is equal to delta x final squared. And so the spring will displace whatever the square root of 3,500 is. Yeah, assuming I haven't made a careless error. Riley?
I'm confused. Why is the spring constant 20? Because over there you put it's 20 newtons over.
Newtons per meter.
Oh, okay. Sorry, they meant newtons over the mass.
Oh, no, that M is meters. I guess
Well, 1/7.
perhaps a little bit clearer, I've written 20.
Sorry.
So how much does the spring compress?
59.16
59.16
Is it-
units?
meters per second? No,
Meter.
just meters.
Meters. It compresses a certain distance.
I thought that was velocity, like changing velocity.
All right, so what we have here is the spring is going to compress 59.16 meters. Now, it's ideal. It gets to a certain point, there's no friction. That spring is now going to release. How far back up the hill will he go when the spring pushes him back?
That's just, that'd just be a cake formula, right?
Will
No.
it also just?
Acceleration is not constant. Pardon?
Will that also just be 59.16 meters?
No.
If the spring is ideal and there's no friction, would go back to the start?
Yeah. That's where he is. That's where he ends up.
Oh.
There's no energy loss, so whatever energy he has at the bottom, because of this, will translate back into the amount of energy he had to start with.
Oh.
He will go on forever. I guess as long as bugs keep landing on. So here's the visual. He starts out with all this potential energy and no kinetic. As he goes down, they sort of go back and forth until he gets down to the bottom and it's all gravitational potential. So that's at this point. So now he has all this gravitational potential. Let's try that again. Starts out with all this gravitational potential and no kinetic. He goes down, they will exchange back and forth, and so at the bottom, he has all this kinetic energy here. He's going, whatever we had before, was it 29 point something
Yeah.
meters per second? Or 31 point something.
31.62.
31.62 meters per second before he hits the spring. Now he has all this kinetic energy just before he hits the spring and no elastic potential energy. And as it compresses, they will switch, he'll lose all the kinetic, it will be transferred into that elastic potential. And then when he gets kicked back, that gets all translated into kinetic. All that kinetic gets translated back and forth into gravitational potential. And that is as close that physicists will get to dancing.
Well, but lessons, like wood, like if a basketball, like it hits the ground more, it slowly loses that much bounce. Wouldn't the same thing out here?
Yeah, if you hit the ground, the ground's gonna dent a little bit. And so you'll lose energy at that point. The ground will heat up a little bit. The harder the surface, the less indentation, probably get a better bounce, but there's still gonna be a little bit of heating up where the contact happened. Was it this group I talked about the
Slapping chicken.
the chicken?
Yeah.
Okay.
The guy cooked the chicken
Oh,
or something.
yeah.
Oh, yeah. Yeah, she said she's gonna watch a video of that.
Yeah, didn't you, I think you watched it yet?
I already watched it.
Ah. Yes, Pratika?
How would you explain that the energy is conserved in the previous cases? Like, it was gravitational potential and then it's kinetic?
Yep.
So,
In conservation of energy, you're changing energy from one form to another, and that's what's happening there.
okay.
It's only, non-conservative is it gets transferred to a different object. So it's still in him.
Either way, it's
Stored in there.
Yes. All right, I'm gonna stop this.